Welcome to AI Frontiers. This episode synthesizes 50 machine learning papers from a single day, December 9, 2025. The analysis reveals not just incremental improvements, but fundamental shifts in approach as the field transitions from raw algorithms to responsible, real-world infrastructure. The story these papers tell is one of a discipline growing up. Today's journey maps the landscape of that day's research. It begins with an overview of machine learning's evolution. It then explores 5 dominant research themes, highlights key findings with game-changing potential, and examines the methodologies researchers are standardizing. The journey includes deep dives into selected seminal papers, and concludes by examining where the field is headed next. Machine learning has evolved through distinct eras. The first era focused on foundational algorithms like perceptrons and decision trees. The second was the deep learning revolution, powered by neural networks and big data. We are now in the current era of integration and responsibility. The frontier involves tackling messy, physical, and consequential real-world problems. The field is expanding horizontally into every scientific domain, while also deepening vertically, building stronger theoretical foundations, and engineering for reliability. The first major theme is bridging the simulation to reality gap. This involves building AI that respects physical laws. Key work includes Spectral-Embedded DeepONets, which solve partial differential equations with a focus on real-world boundary conditions. Another project uses transfer learning from polymer to metal 3D printing data to qualify parts. A third study uses the known physics of an electron microscope to predict model failure points. This marks a shift from digital pattern matching to AI, becoming an integral engineering and scientific discovery tool. The second theme is the sovereign challenge of improving reliability and trust. Research includes work on certified robust data attribution, which provides mathematical guarantees for explainability. Other efforts focus on improving model calibration. So a 90% confidence score means 90% accuracy. Transformer failure modes are being understood through graph theory, and federated learning methods guide models toward flatter solutions for better generalization. The message is clear. Accuracy is no longer king. Reliability is the new sovereign. The third theme is privacy, decentralization, and new frontiers. Federated learning is evolving, with systems like SOFA-FL that self-organize into hierarchical clusters based on data similarity. Groundbreaking work enables provable machine unlearning in fully decentralized networks. A novel privacy risk was identified. Large language models generating synthetic tabular data can inadvertently memorize and output real numeric strings, like social security numbers. Privacy battles are being fought on unexpected, evolving fronts, moving these concepts from theory to deployed practice. The fourth theme is architectural innovation and efficiency. This includes refining Kolmogorov-Arnold Networks, or CANs, for greater parameter efficiency. A seminal paper solves the long-standing graph neural network oversmoothing problem via non-local message passing. For slow diffusion models, researchers train small policy networks to intelligently skip generation steps. The work involves tailoring architectures for specific constraints of physics, scalability, or speed. The trend is one of transformer refinement, not replacement. The fifth theme is domain-specialized generative and predictive modeling. AI is becoming a bespoke toolkit. Examples include designing novel, functional enzyme proteins with lab validation, synthesizing realistic motion sensor data for health monitoring, and weaving news sentiment with financial graphs for stock prediction. Other applications forecast deadly urban heat waves and select the optimal prosthetic heart valve for individual patients. This deep integration requires profound domain expertise, signaling field maturity. Several key findings stand out as game-changing discoveries. The first is the discovery of spectral amplification, which explained why previous data attribution robustness certificates were broken. The introduction of a Natural Wasserstein metric yielded the first non-vacuous certificates, achieving 68.7% on a standard image task. Another breakthrough was the de novo generation of functional enzymes via a model called TPS-GPT. A theoretical unification framed transformers as graph neural networks, explaining failure modes. Clinically, personalized heart valve selection achieved a 26% reduction in pacemaker risk. The methodologies used tell a story about standardizing approaches. Physics-informed modeling bakes known physical laws directly into model architecture or loss functions. Federated learning frameworks enable privacy-preserving training by sending the model to the data. Diffusion models have expanded beyond images to text, sensor data, and weather forecasting. Reinforcement learning acts as a meta-tool for optimizing other models. Graph neural networks remain indispensable for any data involving relationships or structure. A paper of the day is by Shihao Li and colleagues, titled Natural Geometry of Robust Data Attribution, From Convex Models to Deep Networks. The problem was that data attribution scores were incredibly fragile. The key discovery was spectral amplification, which made standard Euclidean robustness metrics meaningless for deep networks. The solution was the Natural Wasserstein metric, which measures distances from the model's own perspective. This yielded the first non-vacuous robustness certificates, 68.7% on CFAR-10. The significance is moving data attribution from a suggestive heuristic to a tool with mathematical guarantees. A seminal paper by Weiqi Guan and team is titled Solving Oversmoothing in GNNs via Non-Local Message Passing. It addressed a classic architectural dilemma. Pre-layer normalization caused gradient vanishing, while post-layer normalization caused oversmoothing. The insight was that not all smoothing is bad. They introduced the concept of algebraic smoothing. Their innovation was a parameter-free, non-local message passing step within a post-LN framework. The result was stable training of graph neural networks with up to 256 layers, outperforming shallow networks. This unleashes the depth potential for capturing complex relational hierarchies. An impact paper by Favos Pascalidis and colleagues is Towards Optimal Valve Prescription for TAVR Surgery. The objective was to provide a personalized valve choice to minimize the risk of needing a permanent pacemaker after surgery. The methodology harmonized data from U.S. and Greek hospitals using a novel leaf-level statistical analysis. The innovation was moving from prediction to clear prescriptive recommendations. The result was a 26% relative reduction in the pacemaker implantation rate in the U.S. cohort. The significance is AI moving credibly from the lab notebook to the operating room, with direct human benefit. Future directions point to greater convergence with scientific discovery methods, where AI becomes part of the scientific method itself. The rise of foundation models for structured data, like graphs and time series, is anticipated. A critical frontier is lifelong and continual learning in open, non-stationary worlds. The Holy Grail remains advancing causality and counterfactual reasoning. Persistent challenges include the last mile of integration and deployment, the need for unified evaluation across domains, and balancing the efficiency-accuracy-trust trilemma. This presentation was created through a synthesis process. Content was generated by GPT analysis of 50 paper summaries from the arXiv preprint server. The model used for research narrative construction was DeepSeek Chat. Audio narration was synthesized via DeepGram text-to-speech. Visual image concepts were generated via Stable Diffusion. The content underwent human expert review with oversight acknowledgement. A caveat is noted. While reviewed, potential oversights may exist. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.